Monitoring at Scale with eBPF, presented by Brendan and Alex from Netflix.
Thank you. It's great to see the hardcore security professionals still out here making it to the 410 talk. Special thanks to the locals who are putting up their first sunny day this whole winter to hear us talk about security monitoring. So I am Alex Maestretti. I manage the CERT team at Netflix. We provide security intelligence and incident response across the whole organization. But our focus is on the product. So that's the streaming service that we host in AWS. I started about a year ago, and when I came on board, I was looking around with the team to see what sort of intelligence telemetry we could get on the security front. So in doing that, I wanted to get some more details out of the instances that were running in AWS, some more details off the endpoint. And so I came up with a standard security architecture response, which was to monitor all of the things, right? And that sounds really great. It works really well, but when working in the public cloud, you have some very direct costs that are involved in that. So I went to the base AMI guys and said, hey, will you push this set of audit rules for me? It's going to monitor all the things. We'll have great responses out of this. And they said, maybe you should go get some more context on that. And what that means is like you might be about to do something stupid. So when you get that response, what you need to do is stop and think and go find someone smarter than yourself to ask questions. And that's when I met my co-presenter here, Gregg, who is a senior architect on our performance team. So I talked to him about what it meant to monitor all the things, and he was able to come up with a very direct cost bill of what that would cost us in terms of compute overhead. And then it was up to me to sort of stop and think about whether that was really in Netflix's best interest or if we needed to find a better way. And fortunately, Brendan has been building open source tools for a long time in terms of performance monitoring and introspection. So he's deeply familiar with the inner workings of Linux kernel. He's been involved with this eBPF sort of movement, for lack of a better word. And so he provided the option of sort of having our cake and eating it too, which is really using eBPF to do security monitoring. And so as I started looking through this, I got super excited about it. I wanted to do some talks. He agreed to join me on these talks. So I think that's our purpose here today, is to sort of cross-pollinate from the world of performance to the world of security and see if we can't sort of build some consensus around eBPF as a great tool to do better security monitoring in the Linux kernel going forward. So that's our purpose. I would say the goals of this talk are sort of threefold. One is the why. Why is eBPF important? We have a lot of great security monitoring tools already out there. Why is eBPF relevant? Why should we be thinking about it? So I'll cover some of that and try and convince you. Number two is how. How does eBPF work? How can you guys use eBPF? And Brendan will sort of cover some of that. The performance benefits are derived from the fact that you can execute in kernel, but you also get safety and stability constraints around that through bytecode analysis and various things. So he'll walk you through how it works, and he'll also walk you through how you guys can use it using the BCC, the BPF compiler collection that he's been contributing to. So it makes it very easy. Within a weekend, you can do the tutorial. You'll be getting very raw data out of the kernel using just Python, essentially. So we'll do the how, and then finally, it's sort of a call to action is, hey, if you guys are interested in this, if we've convinced you this is cool, reach out to us. We're looking for collaborators. We want to sort of build some open source BPF tools around security monitoring on Linux. So with that, the why. Why is eBPF, in my opinion, super important and sort of a sea change in the way that Linux is going to operate in the security realm? Well, we've got all these great existing security monitoring tools out there. Why would we want to build a new one? And it kind of goes back to that intro story I told you about the performance piece, but it also applies quite a bit to the way that you consider your design constraints when you're working in a public cloud environment and when you're working in microservices. So with the public cloud, in our case, AWS, the cost structure is different than if you have sort of a traditional data center where you have perhaps a lot of servers, you have sort of sunk costs. In the cloud, you're buying compute on demand, so memory and processor are very important to you. But transport within a data center is pretty much free, and storage is based on cost. So it might actually be cheaper to store log data off instance than on instance. So there's some interesting sort of trade-offs there that you can think about. And as I started working through that, I realized that maybe we needed a different way to approach things. So my first thought was OS Query, because this awesome product. It applies in the data center, it applies in user land if you have users with desktops and laptops. It's apparently a ticker tape parade is starting. So it works on Mac, it works on Windows, it works on Linux. It's sort of the Swiss Army knife of security monitoring. And for those of you who aren't familiar with it, basically how it works is that it takes all of the security relevant data from various systems and it presents those in tables that you can then query through SQL. So if you know OS query, you don't need to know exactly where the process table is in Linux or in Windows or in Mac. You just write a SQL query and it gives you that information. So a great tool. It's been deployed at scale in a number of places. You can use it as either sort of a hunting tool to jump in and ask questions of things, or you can use it as a monitoring tool through the daemon process. But it still has this idea of sort of batch queries, right? You're writing SQL queries against the tables. So there's more of a pull nature to it. And in theory, right, if you're doing the daemon, you're asking these queries every, say, 5 or 10 minutes, there's a window there for an attacker to exploit on the box, escalate privilege, clean up logs, and even closer to the mic, yes, I can do that. My problem is I am tall. I will get closer. That too close? Closer to the mic. Okay, this is good. This is my first mic appearance. Apologies for the technical difficulties. So, as I was saying, OS query, there's a window there in which, in theory, an attacker could clean up logs and you might miss a detection. So that's what sort of drove us towards more of a push methodology rather than a pull methodology. So I mean, it might be kind of a moot point if you have a very narrow query window, then it'd be very difficult to clean things up in that amount of time. However, just from an architectural standpoint, kind of like the idea of streaming events off of the instance. And I think a lot of folks are going that way, right? You see Windows event logs, you see even Carbon Black announced a streaming sort of detection service. So that seems to be the better way to do things. Another option, OSSEC, I think that was mentioned earlier. OSSEC is a very fully featured HIDS, host intrusion detection system. So it provides you rules and alerting that you can trigger on various either insecure configuration states or series of events that come out, and it will fire off these events and let you know that something's wrong. So it's sort of a streaming model in that regard. However, it's pushing all of the rules and intelligence down to the instances. So that sort of runs into the microservices architecture, right? You want to keep your microservices very lean because you're going to deploy tens or hundreds or thousands of copies of them. So it might not be the best approach to run tens or hundreds or thousands of copies of the same rule set. It might be more efficient to sort of do that at a higher level. But moreover, you have much better context at that higher level. So while on instance you might be able to detect rules quickly and take actions on basic heuristics, again, in this microservices architecture, if you've got many copies running the same set of code, you can sort of look at that as a peer group or a herd. So you're taking these built from source, you're stamping out many copies, they're serving traffic from a load balancer. So as they start to serve traffic, their security characteristics might change, but they're going to stay roughly in a group as they move around. And if one of them starts to sort of depart from that cluster, that might be a performance issue, it might be a security issue, but you should probably take some action. You could terminate that instance, you could quarantine it, you could go give more introspection. But those are some fairly high fidelity alerts you can do based on sort of standard machine learning algorithms. But you can't do that without the context of the whole herd. So you can't do that on the endpoint, so you can't really do that with OSSEC. You need to do that at a higher level. So that's why we sort of moved away from the model of having a highly capable HIDS and wanted to, again, stream events off box and make decisions elsewhere. And that's really what audit-D does, right? Audit-D has been around forever in Linux. It will let you write rules to capture various syscalls, give you a very good view of what the system is up to. But that was where I ran into that performance issue. And there's also some filtering issues around what audit-D will let you do, or what K-audit will let you do filtering-wise. For instance, sockets, right? If I want to monitor all of the network sockets, I can monitor all socket creates, but I get inter-process sockets too. So I get way more information than I really need thrown across the transom between kernel and userland, and that has a performance penalty as well. The Slack guys wrote a great update to audit, Go Audit, which is a rewrite of the userland daemon, which allows you to get a little performance benefit from the userland side of things, output JSON, and do regex filtering. So it solves some of those problems, but as we'll see later in the slides, performance-wise, we were still looking for something a little bit leaner. So sysdig's another interesting one. On the flexibility side, it meets those needs. You can create a chisel to do basically anything you want, but sysdig is throwing everything over that kernel to userland barrier. So to me, it's more of a very useful introspection tool or system tracing tool and less of a security monitoring tool. So that's sort of where we came down from the existing solutions, right? We've got a bunch of great stuff out there. We'll probably still use things like OS query when we want greater inspection, but we're looking for an approach where we have very lightweight, thin monitoring across the entire fleet, and when we detect something, then we turn up visibility. And that's really the only cost-effective way to do it at a larger scale. So for that, we have a new option, and that is this eBPF, which Brendan will now walk you through some examples of how it works.
Okay, thanks, Alex. My name is Brendan Gregg, and I'd like to show you BPF by starting with a screenshot so that you've seen something concrete. This is a very simple tool. It's using kernel dynamic tracing of the cap-capable kernel function call, and it's printing out per event details. You can imagine running this to create a whitelist to see what capabilities your application is using. Has anyone used K-probes before? Oh, excellent. So we have like 10 people. What about ftrace? Linux ftrace? Oh yeah, like 15 people. That's excellent. So this doesn't look that new. The kernel has had things like ftrace and kprobe for a while, and so you can, and I have another toolkit of tools which can do things like this. Where eBPF gets different is that we can run programs on events. Here, this is a bit of a hack, but I've taken the cap-capable kprobe, and I've used another open source tool called argdist, and I am taking the DX register when cap-capable is fired, and I'm doing an in-kernel frequency count. And the output that we see here, so we have the capability 12 was hit 83 times, 21 was hit 5 times. That's nice, but that's frequency counted in kernel using an eBPF map. And that's something that only eBPF can do when you compare it to previous inbuilt kernel traces, like ftrace and perf events. And we can do a lot more. Not just frequency counting things, we can do more advanced filters. So there's been many, many traces for Linux, and I've got a list here. There's been kprobes, which was added a long time ago for kernel dynamic tracing. There was dtrace, which really helped to prove that dynamic tracing was powerful and useful, although that was not integrated in Linux. There's been system tap, although that's been out of tree. ftrace, which a bunch of you have used, that's great. Perf events, which is a great official performance analysis tool for Linux, and so on and so on. There's also been many out-of-tree traces. So there's been LTTNG, sysdig, KTAP, and many more, Intel PIT. Unfortunately, there's not a lot of documentation or use cases getting into all these different traces. I mean, when it comes to kernel engineering, this is the bottom of the basement. This is difficult stuff. When I first got into kprobes a few years ago, I was searching for resources, and I found the code in the kernel, and I found in the kernel tree there is /documentation, and you can read the documentation that was submitted with the patch set, but there wasn't much evidence on the internet of people actually using it. I only found one good reference, and that was from Frack magazine, and it turns out the security crowd really get into it doesn't matter how difficult it is, and there's a great introduction at the top of the article which says, we are hackers. Hackers should be aware of any and all resources available to them. And it's great. So kprobes, at least there's one person that knows kprobes in detail outside of the kernel tree. But I'm going to talk about BPF. BPF itself began life as a packet filter. And if you run TCP dump and you give it an expression and then you add -d for debug, it prints this weird assembly. That is user-defined bytecode that's sent to the kernel and is compiled and executed when those send-receive events happen. And it's executed inside a sandboxed virtual machine. Well, this is really interesting. So there's a virtual machine in the kernel where I can send it bytecode and have it run stuff on my behalf on events. Well, it's really interesting when it's been enhanced so that instead of just send receive, it can be attached to other things, and it can also do more things with its assembly. So the BPF assembly has been enhanced. It has maps now, which are like associative arrays, key value arrays, so we can store things in kernel memory, like when I was frequency counting the capability calls. And we can also do actions, so we can modify the state of the system. eBPF looks like this. eBPF is one of the most difficult programming languages I've ever tried to code in. In fact, I'll confess, I've never had a single raw eBPF program of mine compile. I have had Intercal programs work. In fact, I'm a contributor to Intercal. I wrote the guessing game in Intercal, if you know what that is. So I'm fine with complicated languages, but eBPF itself is really difficult. It's okay because not many people need to know this. There are compilers so that you can write a higher level language and it compiles into eBPF. What eBPF does is it's difficult to get our head around. Like I said, this is a sandboxed virtual machine and it's in the kernel. This is not some third-party add-on that a company has created. This is in Linux, the 4th series of Linux. So if you're running Linux, sooner or later you're getting this weird technology. So far, we've thought of many use cases for it. The company that was originally doing the development, PlumGrid, they were using it for software-defined networks, so that you could write router and NAT controls in kernel and firewalls, and that would become a BPF program that was executed when packets arrived. It's being used by Cloudflare for doing DDoS mitigation, so that servers can accept a higher rate of traffic and drop those packets earlier in the TCP/IP stack. We're looking at using it for intrusion detection, and we're not the only people. There is a company that's using it for container security. And at Netflix, I'm using eBPF for performance observability. To give you an idea of the internals, you write a bytecode program, and that gets loaded into the kernel via a verifier, which makes sure you're not doing anything naughty. So it makes sure the program doesn't do backwards jumps, it doesn't do loops, it doesn't access memory that it's not supposed to access. Then, that can be executed by BPF. The way we want to design it, or the way we are designing it for security intrusion detection is finding all the different events we want to trace, but we can put our finger on low frequency events to make it more efficient. BPF can then send out a per event log that's using ring buffers, and it's polled from user space at a gentle interval, all for efficiency. So what can we monitor? Now, there's been some great talks today at BSides, and we got to see how, for intrusion detection, what normally happens is you look at what the vendor gives you, and the vendor might give you some Microsoft access log or some web access log, and then you figure out how to interpret it and how to figure out what is suspicious on the system given logs. This is different. When you're using dynamic tracing, you pose the questions of the system. This is a little like, I guess as an analogy, the difference between cable television and Netflix. With cable television, you turn it on and you watch what they decide to play you. And that's like consuming a vendor log, consuming what Audit D has decided, for example, on Linux. But with dynamic tracing, it's like Netflix. You're in control. You get to pick what you want to watch. And so when I started doing this slide, I was decorating it with the kernel functions that we can trace for these events. And I realized I'm not going to do that. I'm going to decorate it just with the names of the events, just to highlight the difference in thinking that we're now going through. We choose what we want the instrumentation to give us, not the other way around. So we can instrument all of this. We can instrument shell commands, SSH authentication, crypto initialization, sudo usage, su usage. libpem events are really easy because it has a nice API we can trace. When processes are launched, set UID, privilege escalation in the kernel, any code path that does that, we can trace. We can trace anything weird that's happening in virtual memory. Maybe there's something's trying to execute the wrong page. TCP IP, we can go up and down the stack, and we can trace events. We don't have to touch send receive because that's high overhead. We can trace lower frequency events, and so on. There is a collection of tools, the BCC examples, and I've written many of these. This is on GitHub, which demonstrate that all of the different places we can trace, and many tools are getting added all the time. And so these serve as nice examples. What I'd like to do is just give a quick demo of a couple of these. Okay, so I'm logged on a Linux system. Okay, so I'm on 4.8, but BPF has been around since like 4.4. It starts to get usable. And just as a couple of examples, I'm going to run bash readline. This is instrumenting the bin bash program, and it's instrumenting whenever the bash shell accepts a new line, a new command. And it's doing it system-wide. I don't need to give it a process ID. I can go to another window. And I can type in commands, and I've instrumented it so that I can take a log. I didn't need to run a special version of bash. I didn't need to compile it in any special way. I've just chosen, I've looked at the bash source and I've said, this is the function I want. So I can look in the bash binary and I can say, yeah, you know, I want to trace readline. That's probably got what people are typing. And then I just use this is uprobes, user space dynamic tracing, and I've built a tool to do that. As an example of kernel dynamic tracing, okay, so this is dev PTS1. Okay, so I have one window is watching every single character that appears in another window. So it's seeing it event by event. Does anyone remember the tool TTY Watcher? TTY Watcher, anyone used that before? So I've just rewritten that using BPF. It's very simple, right? Because the kernel is emitting characters to that TTY, and I can just trace those kernel events. I can even do things, if I run vi, this is where the wheels fall off a little bit. So I can see them in vi, but it's kind of not working. I was setting up this demo, I realized I didn't pick a buffer size big enough. So my TTY buffer is only 256 bytes. So I need to change that to be like a kilobyte so that I can catch all the screen writes. Anyway, these are just examples of using dynamic tracing in the kernel. And there's just so many events we can instrument. So I could instrument all of the TCP functions. So there's TCP check space, receive established. The screen's messed up because I was doing TTY Watcher and I had the vi escape characters. So I can trace thousands of events in the kernel and come up with the instrumentation I require. And that becomes the difficult part about using this. It's the questions you want asked of the system. There's a couple more screenshots, but I just demoed some. So there's exec snoop where I can see commands as they are run. TCP connect, where I'm only instrumenting the kernel functions that do connect. So I'm not touching send receive. I'm doing performance engineering, and so that makes me happy because I can keep the overhead very low. You know, wherever possible, we want our network intrusion, our system intrusion detection system to consume less than 1% CPU. Some instrumentation techniques. Firstly, you need to know the questions you want answered, but use the stablest API possible. Dynamic tracing is fantastic. I can put my finger on any software function and begin to write events out. But if I start doing that a lot, when the kernel changes, my programs will break because the kernel changed that function I was instrumenting. There are trace points in kernel space, and then there are USDT probes for the equivalent at user space, and these are the stable APIs. So if we build our security tools using them, they will work from version to version. If they don't work, we can try and find something that might be dynamic tracing, but it kind of has a stable API. Alex had the good idea of tracing the security hooks that are built inside Linux, usually built inside Linux, because they kind of have a stable API. And so we can use them to create intrusion detection systems as well. I was noticing last week that libpam has a very well-defined API. So I can trace libpam, authenticate, et cetera, et cetera. But why we love eBPF is three things. It's safe. The kernel has the verifier. It protects all memory access through helper functions. And it's also part of the mainline kernel, so we're all getting this. It's flexible, so you can instrument anything, anytime. And that means if there's some new zero-day vulnerability out and Audit D doesn't catch it, we can probably write an eBPF program and run it immediately. We don't need to restart any binaries or start anything in a special mode. It's like updating snort logs on the fly. So someone can say, oh, there's a new attack. Here's an eBPF program that will instrument it. You can run it straight away. It's also performant. So eBPF has been designed to do network send-receive tracing, although I try to avoid that. I try to hit up lower frequency events. But it uses jittered instrumentation and other techniques to keep the overhead low. I did a quick comparison between Audit D, Go Audit, and eBPF, and I was doing just the accept system call to see when connections were accepted. And BCC eBPF was about 1/6 the CPU overhead of the other solutions. Go Audit was a little bit faster, but BCC eBPF was a lot faster. But just to really illustrate the difference in overhead, the old way to do this kind of instrumentation is packet capture, but the new way is dynamic tracing or static tracing if possible, where you can put your finger on the event and say, I only am interested in that event. I don't need to do every syscall or every send-receive to keep overhead low. That gives you an idea of the code. And this is all on GitHub, /iovisor/BCC. It's part of the Linux Foundation. You write some C code, which gets run by the kernel, and then Python code to do the user-level reporting. And there is a tutorial online if you really want to get into it, and lots of examples. It gets pretty complicated. So this is a little bit of my TCP accept, where I'm going and digging out bits and pieces to get the IP addresses and ports and whatnot. It's hard, but it's doable. You don't have to write the eBPF assembly that I showed earlier. At least this is C, so it then gets compiled into eBPF. But it's great that this is all possible at all. And I'll hand it back to Alex for the summary.
Awesome. So one correction, I got to give credit's due. The idea to hook the LSM was our colleague Brian Payne's. But I would definitely encourage you guys to go check out that IOVisor compiler collection, because I am not the world's greatest developer, but within a weekend of playing with this, I was getting raw data out of the kernel in a very performant way. So it makes it very, very easy. And that's really our call to action here, is to get more folks playing with these tools and to encourage you guys to reach out to us to maybe collaborate on bringing security monitoring based on eBPF to an open source solution. I'm disappointed we didn't get the illustration done in a professional manner, but here's my sort of take on what I was describing before. Right, you've got the various instances out there, they're producing telemetry, you're looking at them as in terms of a herd and trying to do outlier detection, and then turning up response based on that. I think this is an interesting space. I think we've got a chance in this sort of modern environment of having immutable ephemeral instances that we may not have had in a more general purpose environment. So I'm really excited about what this means for our industry and for security in the data center. So thanks again for sticking around to talk to us, and hope to hear from you guys soon. Bye.
So on behalf of BSides and Fitbit, and for referencing Frac Magazine in a presentation, I'd like to give you both a Fitbit.
Oh, great.
Let's hear it for Brendan and Alex.